Next up, question 15. Almost nobody managed to get this one right, and even here you can see that I didn't get it right until I looked at the mark scheme to check it, and therefore I have egg on my face too, so do not be embarrassed. But here we are. Treat the jumper as a point mass located at the centre of mass, and it shows the position of the centre of mass 1 metre above the platform. Calculate the extension of the rope when the centre of mass of the bungee jumper has fallen through 31 metres. So it's going to fall through 1 metre, okay, and then the centre of mass will be basically at the fixing point, and then it's going to fall another 30 metres, okay, and that's 31 altogether. So after another 30 metres, 1 metre there, 30 metres falling, that gives you 31 metres. Well, if the rope, so basically what that means is that he's from this point here, he's only gone down 30 metres to get to 31. Yeah, and so this is how you do it. You've got to subtract 1 from the 31 before you subtract the 19, and that gives you 11. And it's a bit of a pain, but there you go. Calculate the resultant force on the jumper when he reaches the lowest point in the jump, and it says that at the lowest point in the jump he has he's fallen through a distance of 31 metres, which is this bit here. Now, of course, if you've got 12 for this, which is what most people had, then you're going to have an error carried forward. And this is one of these really good examples of why if you don't show your working, you're going to get very few marks in a really A-level exam paper, because this catches most people out, but it's only 1 mark, and the rest of it just requires error carried forward. So the resultant force acting on the jumper when it reaches the lowest point, basically we know that the extension is 11 metres, and if you put 12, that's fine. As long as you show you're working, you can get error carried forward. So the upward force is the reaction force from the bungee, and that gives us 4180. So it's the spring constant times by the extension. The downward force acting on the jumper, of course, is their weight, which is mass times by gravity, which gives us 735.75. So what we need to do is subtract one from the other, and that gives us 34425, which of course becomes roughly 3,400, which is the correct answer. If you showed your work and put in 12 metres, it would come out to this number, and you'd get 3,800. Doesn't matter then. Alrighty. Calculate the extension of the rope when the jumper's acceleration is 0. So the acceleration will be 0 when the forces are balanced. Okay, because as we know, F equals ma. So we're going to get 0 acceleration when there's 0 force. That means that the upward force and the downward force are the same. So mg equals k delta L, because F equals k delta L. So I know what delta L is, and delta L is mg over k, and that gives us 1.9 metres. Okay, so soon as the rope has extended even a little bit, he's basically got an acceleration. Right. 4 marks for this one. So this is where I like to, this is where if you do the system that I demonstrate to you to do, you save time, you save energy, and you don't make mistakes if you're careful. So the extension of the bungee is 5 metres, and the jumper's centre of mass has fallen through a distance of 25 metres. Use the principle of conservation of energy to calculate the speed of the jumper in this position. So what we know is that the gravitational potential energy, as he falls, is converting to kinetic energy, okay, and elastic potential energy. Okay, so first of all, it's going to be all going up and up and up in kinetic energy, and there won't be any elastic potential energy. Then afterwards, it will start to slow down as this builds up. But the GPE is always going to be equal to these. Okay, well. No, it's not always going to be 2, but as it falls, it's going to convert to this. It's going to convert from one to the other. Okay. So what we do here is we're going to rearrange this equation. Say mgh equals a half mv squared plus a half k delta L squared, because we know hopefully that elastic potential energy is k delta L squared. Once we've done that, we want to basically rearrange all of this lot to make v the what's the word I'm looking for, the subject of this equation. So you can see what I've had to do here. Well, what I've had to do is I've gone, we've got the V there, let's subtract the K delta L first, so that's over there, and then let's multiply V by 2 to get MV, and then let's divide by M to get V on its own, and then finally let's square root the lot. Okay, that gives me the equation for V. Once I've done the equation, now I just chuck in all my values, being careful to do things like squaring and remembering to times by 2 and putting the brackets all right. But it's not very difficult, it's not that complicated, and the answer comes out to 19 meters per second. Okay, so that is how you do it. All right, let's move on to here. So the bungee jump operating tendencies of bungee cord are the same unextended length but with a much greater stiffness. The rope will be attached in the same way. Explain with reference to kinetic energy of the jump and any safety concerns that may arise. So a lot of people wrote a lot of stuff, but a lot of people didn't write anything about kinetic energy, which is really where you have to do this. Okie dokie. So you basically want to say it's the same length. So the rope's the same length, so he's going to say the full distance, so he's going to have the same velocity, so he's going to have the same kinetic energy, something along those lines. Okay? The kinetic energy is then going to be converted into elastic tension energy in a shorter extension. So he's going to fall a shorter extension, then he's also going to stop in a short distance, and if he's stopping in a short distance, then there will be greater acceleration and therefore more force, so there'll be greater chance of injury. Okay? That is question 15.